So we're going to look at hypothesis testing in Chapter 8. Let's recap. We've looked at z-scores and found the probability that corresponded with less than or more than a z-score. We learned about sampling distributions and how they make the central limit theorem work. We've looked at assessing normality by looking at QQ plots, and we started to discuss the t-distribution. Quick note on Chapter 8, I'm going to do things a little bit out of order because I think the book does things in a way that's confusing. So watch the PowerPoint first, then read through the book. We're going to skip chapters 5 and 7, but I will touch on those in other PowerPoints. So hypothesis testing is similar to a court of law. In a court of law, a person is accused of a crime, but they're considered innocent until they are proven guilty. Similarly, in a research study, you're having to prove that there was a treatment effect, but we start with the notion that there was no effect, and the onus is on us to prove that there was. So let's look at the court trial as an analogy for hypothesis testing. The test begins with a null hypothesis, meaning none, or zero, or not, as denoted as h sub 0, stating that there is no treatment effect, i.e. there is no crime. The accused person is assumed to be innocent until proven guilty. So the researcher then gathers evidence to show that the treatment actually does have an effect, and the prosecution collects and presents all available evidence in an attempt to contradict the innocent hypothesis and hence obtain a conviction. Note that in both scenarios, the researcher or prosecutor is trying to prove that the null is false. If there's enough evidence, the researcher will conclude that there is a treatment effect, or what we say, reject the null hypothesis in favor of the alternate hypothesis, which is denoted as h sub a, sometimes h sub 1, that there is an effect. Just like the court will reject the innocence hypothesis and determine the defendant guilty. If there's not enough evidence of an effect, the researcher will fail to reject the null hypothesis. Note that the researcher doesn't conclude that there is no effect, just that there isn't enough evidence to prove that there is an effect. Similarly, the prosecution does not present enough evidence to prove the defendant guilty, the court will find him not guilty. Notice that this does not prove him innocent, but merely there was not enough evidence to conclude that the defendant was guilty. So, this is the beginnings of inferential statistics. And what I mean by inferential statistics is using your sample data to infer back to the population. So a hypothesis is a claim or statement about a property of a population. And remember that measures of populations are parameters, and we use Greek letters for them. So our hypotheses are written in terms of parameters, and we use the Greek letter. So hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. The general goal of a hypothesis test is to rule out chance, sampling error, as a plausible explanation for the results from a research study. Now the book has 7 steps, but I'm only going to present 4. It's a more succinct way of doing things, and there's some extraneous things in the book that I think can be collapsed into 4 steps. Okay, so the first thing you do is you're going to state your hypothesis about the population. And since we do that in the Greek letters, and I'll show you what that looks like. The second thing we do is we set the alpha level. And it's almost always alpha is equal to 0.05 in social science studies. So we'll just use 0.05. That's kind of the go-to. Then we calculate the test statistic. I will show you how to do that with hand calculations, only very briefly, and the rest we'll use SPSS. And then you make your conclusion, and that's something that has to come from you, the researcher, interpreting your output. Okay, so step 1, state the hypothesis about the unknown population. So the null hypothesis, h sub 0 or h naught, states that there is no change in the general population before and after an intervention. In the context of an experiment, the null predicts that the independent variable had no effect on the dependent variable. I like to think of it as nothing's happening here. The alternative hypothesis, or the alternate hypothesis, h sub a or h sub 1, you'll see it in different ways in different books, but that means the alternate hypothesis or the alternative hypothesis, states that there is a change in the general population following an intervention. In the context of an experiment, it predicts that the independent variable did have an effect on the dependent variable. All right, so differences in proportions, which is 8.2, we're going to come back to that. I'll handle that at the end of this PowerPoint. But let's try page 351, number 3. A formal hypothesis test is to be conducted using the claim that the mean height of men is 174.1 centimeters. So what is the null hypothesis? Remember that this is stating that there is no effect or nothing is happening here, or what we know is what is being said we know. So the null hypothesis, and this is how it looks, h sub 0 colon, that is the Greek letter m for mu, which stands for mean, is equal to 174.1. The alternative hypothesis, or the alternate hypothesis, is that there is something happening here, or what we know is different than what is being said we know. Here we aren't saying that it is more or less, just that it isn't 174.1. So our alternate hypothesis, h sub 0, or we could say h sub a, colon, mu is not equal to 174.1. So we don't know. We're not saying it's more, we're not saying it's less, we're just saying we don't know which one it is. But we can make other claims. What if we say that the mean height of men is more than 174.1 centimeters? What is the null and the alternate hypothesis here? So the null would be h sub 0 colon mu is equal to 174.1, and the alternate is that h sub 1 or h sub a colon mu is greater than 174.1. What if we say it's less than? Well, this is easy. It's mu is equal to 174.1 in the null, and the alternate is that it's less than 174.1. Okay, let's do another example. A National Center for Health Statistics report indicated that in the year 2015, Americans paid $3,302 per year on healthcare and prescription drugs. An investigator hypothesizes that in 2021, expenditures are lower due to the prevalence of generic drugs. State the null and the alternate hypotheses. So what is the null hypothesis? The null is that the mu is equal to $3,302, and the alternate is that the mu is less than $3,302. Okay, the second step in hypothesis testing is to state the alpha level, which establishes a criterion or cutoff for making a decision about the null hypothesis. You can have an alpha of 0.01, an alpha of 0.05, or an alpha of 0.001, or anything in between, but the one that is most used is 0.05, so that's the one we're going to use. The critical region consists of outcomes that are very unlikely to occur if the null hypothesis is true. That is, the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. So let's think about that. If I overlay a normal curve here, we have the small part here, the hump comes up here, and then the small part comes down here, right? And so we know that between two standard deviations, 95% of the population will be found there. Region of rejection, when we would reject the null hypothesis, are in the ends. Similarly, if I have a normal curve here, right, I can have 95% over here and put my 5% in the left tail. And I can do the same thing with the right tail. I could put the rejection region over in the right-hand side. This will make more sense in just a few seconds. So remember, 95% of the observations fall within plus or minus 2 standard deviations. So here we are. 2 standard deviations here, 2 standard deviations here. And 97 fall within plus or minus 3, 68 fall within plus or minus 1. So what is strong evidence? Where the chance of that score occurring is small and the evidence could be found in either tail. So the critical value to make 2.5% here and 2.5% here, totaling 5%, where 95% is left in the hump of the normal curve, actually doesn't happen at plus or minus 2 standard deviations. It does if we round, but being very specific, it's plus or minus 1.96. 1.96. So that's 0.025, and if you add 0.025 and 0.025, you get 5%. So we can have a one-tailed test like I showed you before, where the chance of the score occurring is small and the evidence could be found in either one or the other tail. Okay, so we could have it over here, and when that happens, the z-score that is exactly at 0.05 is 1.645. And the same way, if you have a right-tailed test, we call this a right-tailed test because we're looking at the right tail. So if my null hypothesis is that the mu is equal to 174.1, and my alternate hypothesis is mu is greater than 1.741, this is a very handy indicator to tell you which way to look. So it's a right-tailed test, and we're putting all the probability in the right tail. So we're looking at the critical value of 1.645 and the probability value of 0.05. We can have a left-tailed test. What if I wanted to know, or what if my alternate hypothesis was actually no, those men are not that tall? So the mean is equal to 174.1, or the mean is less than 174.1. Well, we follow the arrow and we follow the tail. So we look at the left tail, and this is called a left-tailed test. So this is all, if you find a test statistic, so if your z-score falls anywhere in this hump or anywhere in this hump, you're not significant. It's not a big deal. But if you're way out here in this 0.05 region, past negative 1.645, or here, well, I'm going to get into the two-tailed test in a second. If you're over here, then you are significant. And then we have two-tailed tests, aka also known as non-directional tests. There is no arrow. We have a not equal sign. So we don't know which way to look, so it's just we look in both tails. And so that's negative 1.96 or 1.96 if my test statistic is bigger than this critical value or it's in the region of rejection, then I reject the null hypothesis in favor of the alternate hypothesis. If it's here, I do not reject or fail to reject the null hypothesis. And we'll do this so much, this will become second nature to you. I know it's a little confusing at the beginning. So we compare our sample means, which is our data, with the null hypothesis. We compute the test statistic. This is step 3. We've done this test statistic. I'm just showing this to you. We haven't actually computed anything. I'm just showing you this. But the step 3 is to compute the test statistic and see if it is bigger or smaller than the critical value. So either it's bigger or smaller than 1.96 for a two-sided test or 1.645 for a one-sided test. We're going to let SPSS do this for us, and I'll show you that later in this presentation. But the test statistic, the z-score, forms a ratio compared to the obtained differences between sample means and the hypothesized population mean versus the amount of difference we would expect without any treatment effect. That's what's happening. And I'll show you that in a calculation. So then step 4 is to make a decision. So if the test statistic is in the critical region, we conclude that the difference is significant or the treatment had a significant effect. If that is the case, then we would reject the null hypothesis. If the mean difference is not in the critical region, we conclude that the evidence from the sample is not sufficient, and the decision is to fail to reject the null hypothesis. I'm going to give you some examples to make this more clear. The term test statistic simply indicates that the sample data are converted into a single specific statistic that can be used to test the hypothesis. Now this test statistic can be a z-score, a t-score, an F statistic, a correlation, Pearson's R. There are all these different test statistics, a chi-square. We're going to learn all of them, but right now this is where we start. So let's try one, and this isn't from the book, I'm just showing it to you. A random sample is selected from a normal population with a mean of 30 and a standard deviation of 8. So we're talking about a normal population, which is why these guys are in Greek. Okay, normal population. after a treatment is administered to the individuals in this sample, the sample mean is found to be m, the mean here written in Latin letters, is equal to 33. If the sample consists of n equals 16 subjects, we use n to denote the number of subjects. Is the sample mean sufficient to conclude that the treatment had a significant effect? Now I'm telling you to use a two-tailed test with an alpha of 0.05. It is very rare that we would use a one-tailed test, although it does happen. But we're going to use a two-tailed test for this one. So step one is to state the null and the alternate hypothesis. So the null is that the mean is 30, so mu is equal to 30. The alternate is, and I told you to use a two-tail, is that mu is not equal to 30. Alpha is easy, we always set it at 0.05. Then we calculate the test statistic. Okay, so how do I do that? So we have to, it gets very complicated, and I'm not going to make you do this by hand, but when you're doing sample means, you divide your standard deviation by the square root of the sample size because the data are from a sample. So we're just going to let the computer do that for us. But when we do that, when we're using our sample data, we're actually not calculating a t-score, z-score, we're calculating a t-score. So we're looking at a t-distribution. When you have a large enough sample size, which is about 120, then the t critical value becomes the same as a z critical value, so plus or minus 1.96 or 1.645. But when you have small samples, like 16 people, then your t-distribution degrees of freedom change, which is why we have to use t-tables, and I'll explain that. So here's my formula. The mean of the sample minus the population mean over the standard error. So we say 33 minus 30, which is 3, 8, which I gave you here was the standard deviation, 8 divided by the square root of the sample size, so 8 divided by 4, so I have 3 over 2, and my test statistic is 1.5. So I've calculated my test statistic, and I got a t-score, which can be treated just like a z-score. It falls, this is a standard 1.5 standard deviations away from that sample mean, and it's about right here. Now, we know that the critical values for a z-score for a two-tailed test is plus or minus 1.96, but we're not using a z-score, we're using a t-score. So like we did with the z-scores, you're going to have to use now a t-table. So step 4 is to make your decision. So we go look at the table A3 on the inside back cover of the book, and our sample size was 16, so the degrees of freedom is n minus 1, so we have to look at degrees of freedom for 15. And then you look at the center column for a two-tailed 0.05 alpha level, and the critical value is plus or minus 2.131. Since the test statistic is smaller than the critical value, so here we are at 1.5, and here 2.131 is right here, right? We have the value here, beyond which we would reject a null. It's not beyond that, so therefore we do not reject. We fail to reject the null hypothesis. And we say there is not sufficient evidence to support that the treatment causes a significant effect. And so that's the first and the last time I'm going to make you look at a t-table, that table A3. Henceforth, we're just going to use SPSS, and I'll show you how. So, just to recap, the result is said to be significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. That is, the result is sufficient to reject the null hypothesis. Thus, a treatment has a significant effect if the decision from the hypothesis test is to reject the null. So if we reject the null, it is significant or statistically significant. So, in order to eliminate having to use the t-table, we have to look at the p-value. So the p-value is the probability of getting a value of the test statistic that is at least as extreme as that test statistic obtained from the sample data, assuming that the null hypothesis is true. Like I say here, what does that mean? So what this means is that if there was no effect and the null is true, would we find a test statistic in the extreme ends of a normal distribution? No, we wouldn't. So with SPSS, we just look at the p-value. We know that the extremes constitute 0.05. Either we have 2.5% in one tail plus 2.5% in the other tail for a two-tail test, or we put all 5% in the right tail or all 5% in the left tail. Therefore, if the p-value is less than 0.05, then we know it's in the extreme tails, and we can conclude that the null is false. Therefore, we can reject the null hypothesis. I'll show you what that looks like. We won't be calculating our own experimental data by drawing normal curves and calculating all this by hand. We're going to use our software. So in section 8.3, page 376, number 21, lead in medicine. Listed below are lead concentrations measured in different Ayurvedic medicines. The lead concentrations are listed from meds made in the USA. We're going to use alpha is equal to 0.05 to test the claim that the lead concentrations in all Ayurvedic meds made in the US are less than 14 micrograms. So let's do our hypothesis test. We want to test that the mean is less than 14 micrograms. So we state the null and state the alternate. Step 1. The null is that the mean is equal to 14 micrograms, and that the alternate is that the mean is less than 14 micrograms. I should have had the units. So step 2 is to state the critical value. This is easy. We always pick alpha is equal to 0.05. We will consider the p-value, which is given in the output in SPSS. It used to be called sig, and now it's called the p-value. And so sometimes in some other output, it will still be called sig for significance value, but I want to show you both. The program has changed dramatically in the last 2 versions, so you'll see the old version and the new version in my slides, and where they're different I will change and update, but where they're the same I'll keep the old version, just because all my slides are made. Okay, so what I do is I pull up a blank data set and I go and punch in these values. Oops, the raw data here. Okay, so doing that I get 3, 6.5, etc. That's in data view. I click variable view and I can come over here and give it a name. Now SPSS does not like you to start with numbers. It won't let you. You have to have letters at the beginning, and it doesn't like spaces, so I use underscores if necessary. Now we're ready to calculate the test statistic. We're going to do our first t-test for one sample case, which is what we're doing because we only have one sample and we're testing it against a hypothesized population mean. So our null hypothesis is that the population mean is 14 micrograms, and the alternate is that it's less than that. Okay, so using SPSS, when you see these arrows like this, the way I have it written, it's to do it in the order of the drop downs. So I go to Analyze, Compare Means, One Sample t-test, click there. This dialog box pops up, and you'll have the variable here, which you click the arrow and brings it over. We have the lead level as our test variable, and we're testing against the null hypothesized mean, which is it's equal to 14. We want to see, is it different than 14? So we put 14 here. This little box is auto-checked. We're just going to leave that alone. I'll talk about that in a minute. Okay, so the first table shows us that the sample mean is definitely less than 14. Our sample mean is 11.1 if we round. Okay, so that's less, here it is, mean is 11.05 or 11.1. Now we look to the t statistic. And our t is negative 1.4, right? And we know that a z-value of plus or minus 1.645 for a one-way z-test is required for significance, but this is a sample and a small one, so we use t-values. Okay, so now we want to look at the significance. So this is new in this version of SPSS. It never gave us this 1 and 2-sided p. They give us 1 and 2-sided p-values now. And for this example, we're using a one-sided test, but if it's not specified, we pretty much will always default to 2-sided. But because of this one, it's one-sided. And you can see it's not significant in either one, because in order for this to be significant, it needs to be less than 0.05. And the one-sided p is 0.09. and the two-sided p is 0.18, both of which are larger than 0.05. So we say it's not significant. The p is greater than 0.05. If we were reporting it, we would actually give the p-value. If we look in the back of the book, for those of you who are curious, for the degrees of freedom of 9 in table 8.3, we would need a t-value of 1.833, and we got 1.444. Does it matter that this is negative and this doesn't say negative? No, because they're symmetric. We would be comparing this to a negative 1.8333 for a left-tailed test like we have here. So a little mnemonic: if the p is low, then the null must go. So if the p is less than 0.05, then we reject the null hypothesis. It's not significant. If it's 0.05 exactly, it's also not significant because it's not less than or equal to, it's less than. So if it's 0.06, 0.0527, it's not significant. But if it's less than 0.05, it is significant, and we would reject the null. So, really quick, if I run a test and my friend Gilbert runs a test, my p-value was p is equal to 0.01, so I have 1 penny, and his p-value was p is equal to 0.04. Whose test is better or more significant? Mine, right? Because my p-value is smaller. The lower, the better, correct? Nope, not correct. That's wrong. Why? Because there are two serious limitations with using hypothesis tests to establish the significance of a treatment effect. When the null hypothesis is rejected, we're actually making a strong probability statement about the sample data, not about the null hypothesis. Remember, using our sample data to infer back to the population, and we're finding stuff out about the sample data, but not so much about the null hypothesis. By demonstrating a significant treatment effect, it does not necessarily indicate a substantial treatment effect. And now SPSS finally gives us this without making us calculate it ourselves. It's called an effect size, and it's intended to prove or provide a measurement of the absolute magnitude of a treatment effect, independent of the samples being used. So now we want to look at the effect size, and this one we're going to call is called Cohen's d. It measures the size of the mean difference in terms of the standard deviation. So we've got the mean difference, which is 2.95, and I find that here, over the standard deviation, which I find here. 2.95 divided by 6.46 is 0.46. Now here it's negative because this was all in the left tail. But we're just going to take the absolute value. See, we have Cohen's d and Hedges correction. This is a standardizer, and this says point estimate. We want the point estimate. We're going to take the absolute value, so we ignore the negative, and here we see a Cohen's d of 0.46. Here are our kind of benchmarks. Small effect is about 0.2, medium effect 0.5, and a large effect is considered 0.8 or greater. These can be disputed. I've seen papers that argue against these benchmarks, but these are the ones that everyone gets taught, so we'll just stick with these. Also, it doesn't make a whole lot of sense to report an effect size when there was no effect, when there was no significance, but we're going to do it every time just for consistency and to acknowledge that there needs to be an effect size. Okay, and now back to proportions. I'm just going to cover this very briefly because we're not going to do this very often. So from section 8.2, just some vocabulary. P is equal to the population proportion. P hat, this should be really on top of the P, but it's difficult to make it do in PowerPoint, is the sample proportion called P hat, and it's not to be confused with the P value. So your successes is the sample size times the proportion of successes, and your failures is N times Q, or 1 minus NP. So the 1 minus the sample size times the successes. And I'll show you an example. Here we are on page 360, example 3. In testing a method of gender selection, 10 randomly selected couples are treated with this method. They each have a baby, and 9 of the babies are girls. Using an alpha of equal to 0.05, test the probability of having a baby girl is greater than that of 0.75 or 75%. So our null is that the P is equal to 0.75, and the alternate is that the P is greater than 0.75. So we had 9 successes out of 10 trials, 9 girls and 1 boy. Let's look at SPSS. So I'm going to start here, and I know this is busy, but it's very quick, and we're not going to do this very often, so I wanted to show it to you. So I put in 1, 1, 1, 9 times. That's the girls, and 1 boy. I've labeled it 1 is equal to girl, 2 is equal to boy. I come over here, I go to Analyze, Non-Parametric Tests, Legacy Dialogues, Binomial. And then from here, I slide over here, I have gender, and I bring it over. I'm testing against 0.75, and I have to tell it the cut point is 1. Okay, so the cut point, once you pass 1, you're now at 2, so it's going to test. If I had put 2, it would test 2 against all the 1s. So then, here's the output. It's not very exciting. We have 9 in group 1 and 1 in group 2. The observed proportion was 90% female, 10% male. The test proportion was 0.75, and we see exact sig. See, there's the sig, one-tailed, and it's 0.224. This is not less than 0.05, therefore we fail to reject the null hypothesis. So we've learned that in order to test if there is a significant finding of a study, not due to chance, we have to do hypothesis testing. We've learned that there are 4 steps to a hypothesis test, and once we get to the end, based on our findings, there needs to be a conclusion or a decision made. Before we go any further, I want to just make a note about style guides. The first one is the one that is used obviously in psychology and in education. American Psychological Association, or APA Manual of Style. It is the 7th edition that is in current use right now, and that is the one I am the most familiar with. It's also the one that's the most descriptive about how to report the actual statistics. So I'm going to give you all the reporting in APA, and where I can, I'll also give it to you in AMA, which is the American Medical Association, which is now in the 11th edition. And then there's MLA, which is Modern Language Association, which is a humanities-based style guide, and therefore very, very difficult to find any statistics, because typically the humanities, you don't report statistics. So regardless of what style guide you use, when we report the actual statistics, which I'll show you in a moment, we're going to use APA, and then I'll show it to you in AMA where I can find it. AMA is very prescriptive in terms of how to write out medical things, but not always into the weeds and how to report out statistical findings. So again, I know APA the best, so I'll definitely show you that. When we report out in APA, we're looking at our 1 sample t-test that we did. We have APA and AMA, and you can see that they're very similar, and I'm going to point out how they're different. For both style guides, any statistic that is reported is typically italicized. So this is your t statistic, your mean, your standard deviation, your p-value, etc. Notice in APA the p-value is lowercase, and same for AMA, but the p is capitalized. When you're reporting your t-value, you would say t of 9 degrees of freedom is equal to the actual t-value, negative 1.44. P is equal to the actual p-value. If in the output it shows you 0.000, then you could say p is less than 0.001. You never say 00. You just always put the 1 there. So p would be less than 0.001, or the actual p-value that you found. Cohen's d is equal to the Cohen value, 0.46. Notice there's an apostrophe. Here in AMA, it's t of 9 degrees of freedom, but they write this as a subscript. There are no spaces around the equal sign, which I find very crowded, but that's how they do it. Negative 1.44, comma, p is equal to 0.09. Cohen d is equal to 0.46. Small difference, not very big deal. You can use either. I will accept either. Just know that one day when you're going to publish something, the style guide that is used by the journal is going to be important, and that will dictate which one of these you use. Okay, so when we say state your conclusion, when I say state your conclusion, I mean you need to say in words whether or not you reject or fail to reject the null hypothesis. So let's go back to that 1 sample t-test I'm referring to, our mean. is that the mu is equal to 14 micrograms and that the mu is less than 14 micrograms. In APA, I would say the results indicate that the mean for this sample is not significantly less than 14 micrograms. And then I'd write it just like I showed you. Cohen's d, blah, blah, blah. AMA, the results indicate that the mean for the sample is not significantly less than 14 micrograms, and I'd write it in AMA format.